This lecture is going to reflect some of the history of progress in fluids, which is pretty similar to, or bears some similarity to the progress in solids. So with solids, I'm sure you've read about the history some, that when it came to motion of solid objects, trying to find some way to describe things clearly so it could be made mathematical was pretty tough, in particular when you think about vertical motion. There seemed to be all sorts of different scenarios that would occur. If you had something very solid and streamlined that fell, you could maybe get pretty close to describing the motion mathematically. Whereas if something wasn't streamlined and a feather or something like that, it would fall in some sort of other fashion. And progress was made on a variety of fronts, and sometimes a lot of it's contributed to Galileo, who supposedly went up the Leaning Tower of Pisa and brought different objects from there and saw that they all fell at the same rate, is the phrase that's usually described. And what he eventually said is, first of all, came up with that number, that 32 feet per second squared, and that idea that if we could eliminate friction, that really was true. And Galileo, Newton, and a lot of other people around that time were able to start working towards some defined laws of motion that always worked if you eliminated friction. So fluids, there was tremendous progress made in fluids. If you think about like the aqueducts that were part of the Roman Empire, et cetera, there were some engineers who were able to come up with some ideas that worked pretty well. But ideas relating fluids to pressure were pretty tough to work out. Some good progress was made if the effects of what we call viscosity were eliminated from fluids, and a lot of good ideas actually could come up. So that's what we're going to start with. We're going to do finish off section 6.4 today, and then move on to section 6.5, and finally even get on to section 6.8. So just giving you an idea of what's going on here. If just like for solids, we could ignore friction and then make some good progress. For a fluid flow, if we make the following assumptions: steady, we've done that a lot, okay? Incompressible, we've been doing that a fair amount recently. And then finally, inviscid, and that would mean that viscosity effects are pretty limited. A lot of good things can be figured out. In particular, we know that there's going to be streamlines, okay? And we can actually come up with a streamline function that helps us draw those streamlines and it's related to the velocity. We've already talked about that. In addition, the Bernoulli equation is going to hold along a streamline in that case. And we can write the Bernoulli equation from one point to another point along a streamline and do problem solving. All right. That doesn't, though, help us in some regards when it comes to pressure. There's a little bit more that needs to be done with that. And further progress was made along that line if we can also assume that the flow is irrotational. Okay, so we add that assumption in. And if a flow can be irrotational, which many flows are, then it's sometimes called potential flow, and that's what section 6.5 is about. And we can make some additional notes. So first of all, if it's irrotational, bear with me for just a second, okay, what we can do is we can define a potential function where the gradient of the potential function is the velocity vector, right? So that is something else that we can do, okay? In addition, okay, we can say that the Bernoulli equation applies between any 2 points in that field. It doesn't need to be streamlined. So we can have some sort of field here, maybe a two-dimensional field where we have some sort of streamlines going here like this. Okay, and if we call this point 1 and we call this point 2, we can write the Bernoulli equation from that point there to that point there. All right, and so potential flow, in addition, with this introduction of this potential, velocity potential expression, we can come up with potential lines, all right? And you can read about it in section 6.5. It turns out that the potential lines are always everywhere perpendicular to the streamlines, and the potential lines have something to do with pressure. So sometimes these equipotential lines have something to do with pressure. All right, so what we would like you to be able to do is, first of all, know what's going on with potential flow. It's inviscid, it's incompressible, it's steady, and finally we've got to add the fact that it's irrotational. And then we can do this complete description where we can have the streamline, we can have the velocity potential function, we can think about the velocity vectors, and we can apply the Bernoulli equation from one point to another. So what we're going to do now is work through an example and see how that works out, and think a little bit about when this would apply in nature and when we would have to say, actually, that's not accurate and we have to do something a little bit different. Okay, well, here's an example where we can put together what we've learned in the last couple of lectures, and in addition, start thinking about two things. How is, in this example, how is pressure represented, and how does that compare to reality? So just taking your way through it, let me just read it, and you might want to write down this example and see how far you can get on your own. So I've got some flow and some things about it. It is two-dimensional flow, and it's horizontal. So we've got some flow going like this, going two-dimensional horizontally. Somehow, you could be looking down on the flow from above, maybe. It is inviscid. So yes, this fluid probably has some sort of viscosity, but it's so minor that it doesn't really matter that much, given the situation. Okay, it is steady. Okay, so it is steady flow. All right, and some information about it. You're told that U is equal to 4 feet per second as it approaches some sort of region. That's a little unclear, but imagine, say, like the flow is over here and U is equal to 4 feet per second, and V equals 0. Okay, here's some things we're going to figure out. First of all, what is that flow actually going to look like? What is that flow actually going to look like? Okay, is it incompressible? All right, we'll try to make sure we verify that. It turns out it is, so we're going to write the streamline function. Okay, then we're going to ask, hey, is it potential flow? It turns out it is, although that's going to be part of our job to actually verify that's true. And therefore, what is the velocity potential function? What is the velocity potential? Okay, and then we're going to graph what the book sometimes calls the flow net. And so that is going to be a graph where we're going to have some streamlines, okay, and we're going to have some velocity potential lines that are perpendicular. It's a little bit vague. I didn't say over what range of x and y this equation actually applies, but that's part of the challenge, is to try to do something that represents what's going on. And then finally, we're going to apply the Bernoulli equation between a couple points and see what it says. And that's going to allow us to step back and say, hey, how realistic is that? So before we get going, or before you get going on your own, maybe I'll just get you started on the first part. Okay, what's that going to look like? So let's just imagine like somewhere over here like this, the U is 4 feet per second and the V is equal to 0. So I'm going to go ahead and put an XY plane, okay, where we're going to assume that that is X. Okay, and the U is 4 feet per second and the V equals 0 in this region right here. So I'm just going to draw it below. This XY plane holds wherever. Well, basically that would mean that this U function doesn't have any X in it. So at all X, the U would be 4 feet per second. All right. Okay, what about the vertical component of the velocity? Well, it's 0, so there's no vertical. So what do we have here? We have some flow going along at 4 feet per second horizontally, and that's exactly what exactly what this first statement applies. Okay, what happens as we go further along in the x direction? Well, U doesn't depend on x, so as we go further along, so maybe I could put an x-axis right here, like, or a line of constant x on right there. The U is going to be the same, so we're going to have no change in U. Okay, what about the V? Does the V depend on X? No, it doesn't. So we're just going to have flow that's just continuing going to the right in some sort of region here like that. Okay, so let's go ahead and get working. And the next thing to decide is that flow going to be incompressible? So incompressible, that's the next step we want to take a look at. And we'd like to be able to do it mathematically and also and just by conceptual understanding. So first of all, here's the associated velocity vector, 4 in the x direction, 0 in the y direction. We're only doing 2D flow, and there's a picture of it. So Incompressible, we work out by doing the divergence of the velocity function, and we're wondering, okay, is there still going to be spreading out of this flow? Is there going to be compression of this flow? What's going on with that? To me, it's looking like, look, if this is true everywhere at all x, 4 feet per second, then 4 feet per second, then 4 feet per second with no vertical velocity, hey, there's going to be no spreading out and there's going to be no compression. So it should turn out to be a case without dilation. All right, how do we go about doing that? Well, we do the divergence of the velocity function. Okay. And for our case in ME120, that involves doing du dx plus dv dy. Okay. And that's going to give us a scalar function, all right? And if you just think about it, we're going to get what we're looking for. If you take the derivative of this with respect to x, you get 0. The derivative of 0 with respect to y is 0. So we get 0, and that means that it's incompressible flow. All right, so the mathematics verifies that. What does that mean then? In this case, if we have incompressible flow, we're going to be able to write a stream function, all right? And so, or even in some cases not. I wasn't super precise about that, but we've confirmed it's incompressible, and we're going to write our streamline function. So let's get that up there. Hopefully you're working this out on your own. Okay. Yeah, bear with me for a while. So hopefully you have these in your notes, and you can refer to it. I remember last time I talked about, hey, why don't you have a chapter 6 summary that you can always pull out. And this would be a valuable, these would be valuable expressions to write. Hopefully this one here we can just take a look at really quickly and what that means. That means if the partial of our streamline function equals the u value, which is 4, then we get that our streamline function, okay, needs to be equal to 4y plus a constant, or more precisely, a function of x. Okay, v is equal to the negative of the partial of the stream function with respect to x. So for me, it's helpful actually to write it, solve for the partial of the stream function. So dv dx is equal to 0, okay? So probably the partial of our stream function. So our stream function that we get by going backwards from that, okay, is going to be equal to, it could be a function of y. And if we take the derivative of that with respect to x, we're going to get 0. So then we try to take these two results and put it together. 4y, and here equals 0. And just with a little bit of thought, hopefully you get, or can convince yourself that the stream function for this equation is going to be equal to 4y plus some sort of number that's just a constant. That constant is arbitrary, so we just say, we traditionally call it good. If you were actually, say like on a quiz or a test where I was grading your written work and say the stream function is 4y plus a constant, that would be just fine. And it's worth checking really quickly to see whether that's right, okay? If we take the partial of this with respect to y, we get 4, and that is the u velocity. If we take the partial of this with respect to x, we get 0, and that's the y velocity. Okay, really good. So we've got that. Now the next question is whether there's a potential, whether this is potential flow. And we've got almost all the characteristics, but we haven't verified that this flow is irrotational. Intuitively, I hope you look at that and say, hey, that's probably irrotational flow. If this flow actually just holds in a region of the xy plane, and so this moves, this picture of velocity vectors would move down here like that. That sure doesn't look like rotation to me. But let's go ahead and verify that mathematically. All right, so for rotation, we do the curl of the velocity vector. And remember, curl involves cross derivative. So we end up doing the partial of the velocity vector of v with respect to x minus the partial of u with respect to y. Okay, and we don't even need to do any math to take a look at that. If you take the partial of v with respect to x, that's 0. The partial of u with respect to y, that's 0. So that means that this is irrotational flow, and so we're going to be able to come up with that goal of getting a velocity potential function. Okay, so basically what you're trying to do, I hope that you eventually start thinking, okay, if I'm supposed to get this velocity potential function, I'm going to go backwards from the velocity function to come up with a scalar function that ends up, when I do a del to it, ends up getting that. But that may be a little while. To be perfectly frank, as I said last time, this is not something I do that much professionally. In some cases, I wish I did, because I think flow modeling is a very interesting topic. But what we want to do basically is we want to say, hey, the gradient of the velocity potential function, and let me get that up there really quickly, is going to be equal to the velocity vector. So that's that basic idea that we come up with the velocity potential, and if we do the gradient, not the divergence, not the curl, we end up getting the velocity vector. And you can see then what we actually want to work out. We want the partial of phi with respect to x to be 4, and so that would mean that our velocity potential function would have to have a 4x in it. Okay, we'd have to have a 4x in it so we can get that. And of course, it could have some sort of function of y. Okay, and then we also want the partial of our function with respect to y to give that term right there to 0. So in addition, it's also going to be true from that that it could be equal to some function of x. Because if you take any pure function of x and take its partial with respect to y, you're going to get 0. So then we try to put these two things together, and we get that our velocity potential, okay, is going to be equal to 4x plus some sort of constant, okay? And of course, that constant is arbitrary. So the traditional thing to do is just say, if the constant's just a number, we're going to leave it like that. So there is our velocity potential function. All right. So then the next task on the list of things to do would be to take those two bits of information and try to give a picture of what the velocity fields look like. So what we're going to try to do is graph streamlines, and then after that we'll try to do equipotential lines. So streamlines, taking a look at that really quickly. Here's our equation. Here is our streamline function, and that leads to streamline equations. Excuse me, sorry about that. Bear with me for a second. So sorry about that. So we're going to set this 4y to equal to various constants and try to come up with equations and try to make life simple on ourselves. So I'm going to choose 4y equals 4. Okay, for a first thing. So what would that graph look like? Well, hopefully you can do it in your head and see that's going to imply that y equals 1. So we need to graph the curve or line y equals 1. And that is a horizontal line going through y equals 1. And you got to bear with me because I'm a little bit off at an angle. My line's not going to be perfectly straight, but we would have a line like that. There would be a streamline. And you could do several others, okay? You could take this 4 and change it into 8, and you're going to get y equals 2, okay? And just imagine that I'm doing a great job drawing, and that line is perfectly parallel. I could do 4y equals 12, and I'll get a line at y equals 3. Okay, and et cetera. So we'll just get a bunch of parallel lines, right? Of course, this is not a great example in that revealing something all that complicated. It's really more like verifying that the math works, and it is working in this case. We had this flow that was horizontal, it was steady, and everywhere the horizontal velocity was 4 feet per second. So we could even actually put a few arrows in there to help us out. These streamlines would indicate flow to the right. All right. So it's some sort of region of the XY plane. We can do a few above, a few below, and that would give a feel for what's going on. So let's go ahead and do the second thing. Let's get the velocity potential in there. So the equipotential line. So the same idea. There's this potential expression. This is a streamline expression. We set it equal to constants. This is a potential expression. We set it equal to constants. And so let's make life easier on ourselves as well. Let's just pick 4, just because the math works out easily. Well, if we're going to try to graph that, we might want to simplify it first. So we get x equals 1. Okay, so there would be an equipotential line at x equals 1. That's a vertical line going through x equals 1. I'm going to graph it like that as a dashed line. So that would be one of our equipotential lines. Okay, we could also do 4x equals 8. So we would get an equipotential line here like that, and then another equipotential line at etc. And we would get a bunch of equipotential lines. All right. So as we keep moving through the semester, I'm going to ask you to do more complicated functions, but that is your goal. Again, the book calls it a flow net. We've got our streamlines and we have our equipotential lines, and we want you to observe that at every single point you draw it, if you do a careful job, the potential lines and the streamlines are perpendicular. The potential lines and streamlines are perpendicular. Okay, so the last thing to do is to think a little bit about pressure. Okay, so by the way, I would think about this maybe as some flow of water in a very, very large pipe where the effects of friction are not all that great. And so we could imagine that we would have streamlines of water going in that pipe. Or maybe this could be some wind a fair distance above the surface of the earth, and it's moving parallel to the earth, but the effects of the no slip condition are not really affecting that wind all that much. And so we end up just getting a nice parallel flow like this. Okay, the equipotential lines are telling us something about pressure. And let's just go ahead and remind ourselves of what the Bernoulli equation looks like. What you might want to do is, while I'm writing, is try to visualize all 6 terms of the Bernoulli equation and then remind yourself a little bit about it. Okay, so here's one version of the Bernoulli equation. We can go to some point and we can take a combination of the pressure energy, the velocity energy, and the elevation energy and say that's going to be constant as we move. If we move from one point to another, from one point on a streamline to another point on the streamline. And then the new additional fact is that if we have potential flow, and indeed this is potential flow, we could actually go from one point to another point, and that's actually going to work out. Those 2 points don't need to be on a streamline. Okay, so if I were to do all 6 terms, I would have the same 3 terms over here with subscript 1. All right, so we want to think about it before we get going. Is there any way we could simplify this equation going through it? So the main thing to think about is, in this case, we specified that this was horizontal flow. Okay, so we were essentially looking down on a plane where we see this water flowing, on a plane where we see this water or this fluid that does, where viscosity is limited, flowing horizontally. Okay, well, if this fluid's flowing horizontally and either moving up or down in elevation, then we could simplify the equation a lot by eliminating the vertical terms. So what I would like you to do then is go ahead and pause the video and see if you can write the Bernoulli equation with the vertical terms eliminated and thinking about applying it to this particular flow regime. Okay, so you could have written it any way you wanted, in either order if you wanted to, but I, for reasons that you'll see in a minute, wrote this expression, wrote it with the 1 term first and the 2 term as well. Okay, so let's just go ahead and see if we can apply that. By the way, I'm missing a subscript over here. This should be V2 squared, where, again, in this case, V doesn't stand for the vertical component of the velocity. It is the total velocity, the combination of VU and V. All right, so we're going to try to, the goal was to apply this to this velocity flow field, and see if we can derive some sort of conclusions about that. So what I would like you to do for just a second is just say, let's say we call this point right here 1 and this point right here 2. Could we derive some sort of conclusions about pressure from those 2 points, from point 1 and 2? And a couple things for you to think about. Well, probably the main thing to think about, at least I think, is to work a little bit mathematically. We could solve this equation for P1 minus P2. We could take P2 and put it over on this side here, and then take this term right here and move it over to the right. And so that's what I'm going to do. I encourage you to do that yourself and see if you can derive the conclusion about the difference in pressure between 1 and 2. So a little bit of algebra and a little bit of thought. I'm doing my algebra, and I'll get it up there on the board. I'll get that up there for you in just a second. Okay, so I solved that equation for P1 minus T2, and that's basically saying, hey, what's the difference in pressure going to be in this particular case? And if I did my algebra correctly, I'm getting 1/2 rho V2 squared minus 1/2 rho V1 squared in that case. All right, well, can we actually figure out something for the right side? And that looks like a pretty daunting calculation to do, but it's really not that bad. The first thing to note is we actually know V2 and V1, and we can actually say something about the densities. So let's start with the densities. The flow is termed to be incompressible, so the density here and the density here are going to be the same, and hopefully you remember that from the Bernoulli equation. Okay, how about V2 and V1? Well, if you go back to the original velocity vector, this is saying, look, the velocity is for everywhere. Everywhere, the velocity is for here, 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 here. That fluid is everywhere moving with 4 feet per second to the right. Okay, so if you go through and just plug in the same density in V2 and V1 there, this whole term over here is going to be equal to 0. All right, and so your conclusion from that is P1 is equal to P2. All right, so that would mean that the pressure here of the fluid, the static pressure here of the fluid and the static there of the fluid would be the same. Okay, well that actually is going to be true if we have inviscid flow, okay, if it is steady, irrotational, and everything else that assumption that we made in that case. So it turns out it matches reality. But the unfortunate situation is that a lot of times we are interested in cases where there are viscous effects, and therefore the pressure does change. And that means that we need another type of modeling. And that actually is, as I was talking about at the beginning of this lecture, that actually reflects the history of all this, is that just like with solids, if you eliminated friction, you could come up with some great modeling that made a lot of sense. For fluids, if you could eliminate viscous effects, you could come up with some modeling that in simple cases affects what's going on. But pressure ended up being a huge issue in the history of fluid dynamics, understanding what's going on with pressure. So in this case, we get some results that can be valid about pressure. That in that case that I did right here, the pressure would be the same everywhere in this flow. There's some really nice examples in the book where the pressure does vary, and you can make sense of it with an inviscid fluid. But if we add the effects of viscosity, this approach doesn't work, and that's our next step, is start adding in viscosity. Okay, so before we get going, quick aside. Two items. First of all, finishing off the rest of the semester, I'm sure you have lots of questions, and I'm trying to work towards getting them answers to you. But basically what we're trying to do in this semester is do parts of chapters 1, 2, 3, 4, 5, 6, 7, 8, 9. And today's lecture is pretty much going to take us through the end of chapter 6. And then we'll start working on chapter 7. As far as, the syllabus talked about a quiz 2. Quiz 2 is not going to include anything from chapter 7. It will be basically on homework number 6 and homework number 7. And I think it's going to be next week, the second meeting of class. And I'm probably going to try to run it using Canvas. More about that later. But rest assured that if you have completed number 6, I will be posting solutions to number 6, and are working on number 7, and get, as you get early in next week, get a lot of number 7 done. And then as we approach the quiz, you have number 7 done. That's going to be what you're going to need to do. As far as the end of the semester, I would ideally give you a test 3 that would get you a little bit on everything from those terms. So and hopefully eventually you'll be remembering, oh yeah, chapter 4 was about this, or chapter 5 was about that. Hey, how about chapter 2? What was chapter 2 about? Chapter 2 is about fluid statics. So let me just just wanted to take a quick aside and talk about that really quickly. So we talked about U-tubes, and so hopefully you can really quickly remember what would happen. What if we took some water and started pouring it in on this side of the U-tube? How would actually things work out if we poured a bit and then stopped? So, the idea that we had is that, you wouldn't end up with something like that. You wouldn't end up with uneven levels in there. The water would actually seek its own level. That's something that we ended up talking about. And we can really analyze that using the idea of pressure. The pressure here, if this side's open to the atmosphere and that side is open to the atmosphere, those two pressures are the same. So it ends up equalizing, right? What if we changed the configuration a little bit? What if we had a tubing like this where we poured some water in the middle? How would that end up working out? Okay, and once again, all three openings are open to the atmosphere. Well, hopefully it would, you get the same idea that we would have three levels that would all be equal, all right? And the idea then that, again, there is that the push is the same on all three levels, so it ends up actually equilibrating. All right, well, I need to give our chicken some water, so let's just go take a look at that if that's really true, and hopefully make a little bit more progress on understanding some stuff about statics. All right, so we have one of these real typical chicken waters. And obviously, these are for chicks, so our chicks are about 6 weeks old. What we're going to do is I'm going to invert this, so it doesn't look exactly like that configuration I showed with a middle line and then a line to the side and a line to the other side like that. But when I invert this, there's going to be a column of water in the middle, and then the water can come to this side and that come to that side. And so to me, it's looking like this is not deep enough that we're going to get spillage, that it's going to spill over when I turn it over, because I've got a fair amount of water in here. I don't have food coloring, but you got a line water going all the way there like that. And if it's going to, if you imagine inverting this, if it's going to lower, it should be enough to spill. So let's just be careful. I don't want to get my nice laptop from Sac State messed up, so I'm going to give that a shot. And here we go. So you can hopefully see that the water is going down. You see that bubbling, okay? And you got to excuse my camera work. I don't have someone else with me, but just bear with me for a second. I'm going to put it down and move it for you guys so maybe you guys can see. Okay. So looking there at it, it's actually stopped. So the water level actually didn't up spilling. And again, it would be great if I had some food coloring in this. But if you take a look at this column right here, got something in there that's interfering just a little bit. Hopefully you can see that line bouncing back and forth. We've got a pretty substantial column, so our column of water is higher than the water on either side. So what could be going on with that? Well, if you think back about what's going on, that would be, first of all, if you think in terms of pressure, we ought to be able to say, okay, the pressure at the bottom there is basically balancing that pressure up there like that, plus the column of water. So this pressure that's on the outside is large enough to hold up this column of water. And if you think about what was going on earlier when I had it the other way around, when I had it inverted like this, okay, down at the bottom, there was no air in like that, right? Air right there like that. So when I took this and inverted it, okay, we ended up essentially, as this moved down, getting a partial vacuum at this point like there, and that is very, very low pressure. So in this case, there was very, very low pressure above here, and the external pressure was enough to hold up that water. All right, so what we had outside, for starters, is essentially equivalent to this. Looks like a prescription for disaster. We have all, when I tipped over that container, had all this water up over here, and it's going to lower, and it felt like that, this side over here was not high enough to contain. So the water level is going to keep lowering, 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 and the water level is going to come up here like this, and eventually we're going to get spillage, and that didn't happen. So what actually did happen, let me get that drawn in there and give you maybe a little bit more on the explanation. The water level ended up coming over here like this, okay, and in here we had a higher water level there like that. And so I could just do a little scribble in there to get, sorry about that, to get the water in there. Okay, and the explanation again, okay, remember we would put a horizontal line over here like this, okay, and if I ended up calling this point right here B, and this point right here, A, like that. Okay, the pressure at this level over here, sorry about that, the pressure over here, which would be atmospheric pressure, would be the same as that. So that would be atmospheric pressure here like that. Okay, and so this pressure over here is enough to hold up that column of water. And our intuition might be, wait a minute, that's should be atmospheric pressure air as well. But no, actually it's not. It was closed. You saw a little bit of bubbling, and so there was a little bit of air here, but not very much, not very much. And if you remember our ideal gas law, that PV equals RT, okay, or pressure is RT over V, there's actually very, very low pressure in there because there's hardly any air molecules at all. It was like very, very low density air. And so this is what would be called a partial vacuum. And so the pressure up here is negligible or pretty low. So the pressure over here is enough to hold up over this column of water. And actually in the history of fluids and figuring things out with fluids, this idea of taking a column of water, okay, or actually some sort of column, and inverting it was really a major step. Taking that column and actually inverting it was a major step. If you use something like mercury, you ended up, when it was inverting, okay, you ended up, as that fluid lowered, you ended up getting a vacuum up here like that. And that ended up leading to ideas about, hey, can we make this vacuum stronger? Can we do a better job with that? And soon that led to a whole host of discoveries in fluids. All right, so the next thing on flow is we're essentially moving on to section 6.8, where we say, hey, let's take into account viscosity. So some of those conditions that we had earlier, we're going to relax. In particular, we're going to say that the fluid has some viscosity. So what difference does that make? Let's go back to what if we assume that it was inviscid flow. And this is a classic type of flow that you see sometimes where we have a fluid and it goes over the top of some sort of surface. And I see this all the time when we're putting collectors on the top of solar collectors on the top of roofs. What's the flow pattern going to be like over this roof? What's going on? Okay, well, in the previous example, we assume that there are no frictional effects, etc. If you take a look at this flow field, it's just going to continue going to the right like that. And there's going to be no change in this flow due to interaction between the flow and the surface there like that. All right, and that is pretty good in some cases, but not always realistic. So what difference is it going to make if we add in viscosity and do a little bit more general assumption? And I've got these differences to fill out. So first of all, to reminder, we're going to be really considering the no-slip condition. We're going to consider the no-slip condition. So there's going to be a layer here where this fluid's not going to move at all. That fluid's not going to move at all. So get that up there. We're going to consider no slip. All right. Secondly, there is going to be shear. So if I think of this layer here, this second layer up here like this, ending up going over there like that, okay, it is moving past some stationary fluid, okay, and viscosity is basically the adherence between adjacent layers of fluid. So this fluid right here has essentially adherence to the fluid below. So if I try to move it that way like that, if I try to move it that way like that, there's going to be resistance to that. So there's going to be shear. So we've got to take into account shear effects, which we didn't before. Earlier in the semester, we said that the shear is going to be equal to the viscosity times the partial of the horizontal velocity with respect to y. Now that was in a very particular physical situation, but that's a good reminder that in some cases we can calculate the shear using that. Okay, second thing that we're going to note is that there might be a split in behavior in some cases. I wish I had put more vertical lines, more horizontal lines like that to indicate velocity, but hopefully it makes sense to you that if I take a look at this velocity vector right here like this, if it were sufficiently high, let's make this distance like 20 feet or whatever, it's not going to be affected by that very thin layer down below that's stationary, okay? And the same thing might be true for this vector right here like this. It might just keep going. Whereas down here at the surface, it might be ended up being affected. And that leads to the idea that we can split the flow into two regions in many cases. We can have a region where a surface actually makes a difference and affects the fluid, and a region that's free of those effects, okay? The region that's free of those effects is sometimes called the inviscid region. And the region where there are effects are going to be called the boundary layer. Now, I'm no expert on the history of fluid mechanics, but fluid statics got worked out really early history-wise. I do know that. And in addition, I know that the assumption, hey, let's ignore frictional effects and we can get a good description of what's going on, that might be considered the next biggest development. And then the next biggest development after that was the insight that, hey, we can divide fluid flows over surfaces or in pipes or conduits of some into two regions, an inviscid region where the effects of viscosity and the no slip condition don't apply, and then a boundary layer where they do. And that was a huge development. Okay, because we have this sliding effect where there is some fluid that's stationary and some that's sliding over the top, we're going to get rubbing, and that is going to be friction. So we're going to consider friction in our analysis of what's going on. Okay, in the previous examples that we did with inviscid flow, we could get delta P due to velocity change. If you think about the Bernoulli equation, we can get delta P due to velocity change. But now we can get decrease in pressure due to friction. Pressure is like a form of energy. Friction takes away the energy. So we can also get delta P even if there is no change in speed in some cases. Okay, and that's the next to last thing. And then the last thing is about the nature of the equation. So I just want you to have heard, come out of ME 120 here having heard this term. And probably on one homework, I'll ask you to actually look at them. The equations become quite a bit more complicated, and they're called the Navier-Stokes equation. So if you go on to graduate school and you take a graduate course in fluids, first, second, third lecture, the professor is going to say, hey, let's get the Navier-Stokes equations up there, and they're quite complicated. All right, but what do we do in ME 120? What we try to do is take a look at some particular equations and see how these ideas pan out. We're not going to start with the Navier-Stokes equations and actually derive the results, but they too come from the Navier-Stokes equations. So let's take our first example that we're going to look at from chapter 6, and it's going to be a real classic one. I'm going to do an overhead view of a pipe. And I'm going to imagine some fluid is entering that pipe at uniform flow. Uniform flow, a great term to be really clear about. That means the flow is all in one direction and everywhere at the same speed. Okay, so the blue represents the pipe and these represent velocities. What's it going to look like if we're doing the inviscid stuff? Okay, so there's no viscosity effects and we don't worry about friction, et cetera. Well, once again, that's that same example where we just have this fluid going across here like this. There would be streams like lines like this. There would be equipotential lines here like this. Okay. And we actually, that example we did earlier in class, we found that the pressure, sorry about my writing, we found the pressure at all those points is going to be the same. All right, well, how's it going to differ actually now if we take into account of viscosity? Well, first of all, we can't do equipotential lines. We can't do equipotential lines, and we're not going to worry about that for right now. Okay, but let's just get back to more like understanding of fluids as opposed to mathematical stuff. First of all, what's going to happen to these two portions of the fluid flow as they go in? I'm envisioning them as right next to the pipe wall. Well, there's going to be stick in there like that. There's going to be stick in there like that. Okay, and so these bits of fluids are actually going to have to move up and conversely down over here like that to get in there, because this fluid right here is stationary. All right, and with some thought, we'll work on it another day in more detail. In order to get this flow, let's say like this is 5 gallons per minute. In order to get this flow, what we're having is this 5 gallons per minute fitting into a smaller area. And because of continuity, as you thought about before, this middle region is going to have to speed up a little bit to make up for that. So what we're going to have is we're going to end up getting a region in the middle that speeds up a little bit and a region out the edge that's slowed down because of a combination of the no slip condition and the viscosity. So very, very different than what we assumed before. In addition, what we're going to end up getting is we're going to get a decrease in pressure as we move down the pipe. And all those are really, really practical things. If you, many of you who work in fluids, one thing you'll work with is mechanical engineers, you'll work with pipes and ducts where you're connecting things like car engines to radiators, et cetera. And you're going to wonder, okay, well, what pressure is it going to take to get that flow through that pipe? And so this is a very useful example and application. All right, well, section 6.9 does a lot of different cases where there's viscosity. Pretty interesting section to look at. Ideally, if we were to pick one case, we would choose pipe flow, but it's a little bit easier to start with to do fixed parallel plates. And in addition, the case where the flow is laminar. So remembering that definition, laminar is where there's layered flow, there's not swirling going on like we saw behind that car. So we're not going to have the fluid going so fast and have other conditions that lead to swirling flow. Okay, what we would like to be able to do is A, visualize what that's going to look like, and B, also do a little bit of problem solving. So these are these fixed parallel plates. Okay, and we're trying to push some fluid down in between them and have the fluid come over here like that. So basically, I'm just, for starters, what does the velocity profile look like at this first point right here, maybe a little bit further down the pipe, and then as we go further on. So just going through that really quickly, I'll let you look at some pictures in the book, but basically what we're going to have along here is, remember, at all points along there, we have this little boundary region. Well, actually, I should just say this no slip area. So this fluid right here has to speed up it a little bit to get around there. And this fluid down here needs to speed up a little bit. Okay, but there might be a region in here which is sometimes called the inviscid core where the fluid flow is not affected. Okay, but I'm sorry that my drawing's not super clear, but if this bit of fluid now is being slowed down because of viscosity in the no slip condition, its slowing down is going to affect the fluid next to it, etc. And so we're going to get a chain reaction where as we end up going further and further and further down this passageway, more and more fluid is going to get affected. And this inviscid core is eventually going to disappear as the viscosity effects penetrate further and further. So this region is called the regioning of developing flow. And then as we get further down, some distance down, we'll reach what's called fully developed flow, where we have zero velocity here and zero velocity here. The stuff in the middle, by the way, this dotted line going down the middle is supposed to represent the midpoint between the two plates. In the middle, it's going quite a bit faster. So I'm going to draw that velocity vector like that. Okay, so what does it look like in between? Well, that's kind of an interesting thing that's actually proven in the book, in most fluids textbook. You end up getting a parabolic-like profile where you get zero speed here at this end and zero speed at that end, and then the velocity gradually builds up on either side of the midline with a maximum velocity at the midpoint. Okay, what if this keeps going down further? Well, another interesting idea is that once we get to this point where we reach this parabolic velocity profile, we're fully developed. So further down, we're going to end up getting the same exact shape and the same velocities. So we're going to settle into some sort of U profile that's parabolic like that. Okay, my drawing's not great. I'll ask you for the next homework to look at some drawings in the book. All right. Problem solving. What are some things we would like to figure out actually if we were designing a system where we're trying to put flow in between plates? Well, one thing we would like to do is relate the incoming flow, let's say this is 5 GPM or something like that, to how fast it's going to be going down. The faster fluids move in passages, the more noise we get, the more friction we get, and the greater the chance of turbulence. So that's an important calculation that we would like to be able to do. So we would like to be able to figure out what this maximum velocity is. And that's in 6.9.1. We're not going to do that right now. We'd also like maybe to be able to graph the profile. That is something that could be of interest. And finally, because there's frictional effects, now we're going to, the fluid that's flowing down here is going to be losing pressure as we go. down. And so if we want to actually push it through, we're going to have to give the fluid enough pressure here so it can make it through that pressure loss. And that is a very, very important practical thing. So what is the pressure loss as we go down? Okay, so for today's lecture, what's good enough is going to be able to work with equation 6.134. So this is an equation you're responsible for. You can look it up in the book, or you can pause the video right now and write it down. So the first term is giving us, it's basically a formula for the velocity profile that relates it to the viscosity and to the pressure gradient. So this is giving us u at y, and y equals 0, get my hand out of the way in a second, is going to be the midline going there. So up above here, we're going to have positive y's, and below that dotted line, we're going to have negative y's. Okay, so we're going to have a u at y. This is a function that gives us a u at any y when we're fully developed a flow. 1/2 times the fluid viscosity. This term right here is very, very crucial. This is the partial of the pressure of the fluid with respect to x. So how is the fluid changing as we move the x direction is the horizontal direction. So as we move this way, what is happening to the pressure? And if you think about what we've been talking about, that pressure should be decreasing. And then this is y is our distance, our position relative to this axis, and h is the distance from the midline, the mid-axis, to the plate. So our plate opening actually is 2h, is actually 2h. All right, that's not crystal clear, and I think just doing a simple example will help us out. So let me get that example up there, and then we'll see if we can finish off the class by coming up with some reasonable numbers. Here's our example where we've got parallel plates. We're going to have some water that we're going to try to get in between those parallel plates. And the distance, the vertical clearance between the bottom plate and the top plate is 5 centimeters. In addition, we're told that this situation is set up so that the maximum speed of the water in between the parallel plates is 5 meters per second. So all that stuff over here are the givens for the problem. All right, what I'd like us to do is see if we can visualize the flow. Let's see if we can graph u at y to represent what's going on with the velocity profile. And then for practical purposes, we're going to figure out the pressure drop rate. So as this water moves down here like that, at what rate is it losing pressure? And that will tell us how much we need to pressurize it to get that opening. Okay, so first thing, visualizing what's going on. I don't have a great demonstration for you or anything like that, but just you know, obviously, we've got these two plates and they're about 5 centimeters, which is about 2 inches apart. And we're trying to push some water in between those two plates. We're trying to push the water in between those two plates. Is that a lot of water or not a little bit of water? Well, 5 meters per second is pretty fast. That's 15 feet per second. So that water in the middle is going really, really fast. The water at the edges is, well, there's the no-slip condition, so it's not moving at all. And we have some sort of transition between the speed of the flow at the edge to the speed of the flow at the middle. And representing that, we want to end up graphing u at y. So we want to graph this equation right here, u at y, 1/2 mu dp dx, y squared minus h squared. Well, you know, before we get going, actually, we might think, well, wait a minute. We don't have dp dx. We can look up mu for water. We don't have dp dx, and that's going to be hard to graph, okay? But what we do know is we do know that it is parabolic in shape, and we know what the u max is. So that's actually been given. So what we could do is just try to focus more on getting our xy plane correct. So let me just draw a quick xy plane. Okay, so y equals 0, okay, y equals 0 is the midpoint of this passage, the midpoint of this passage. So how high can we go up in this case? Well, we can only go up 2.5 centimeters, and we can only go down 2.5 centimeters. And so I'm going to get those numbers up there. I'm going to just do it in centimeters, 2.5, and this is negative 2.5, so that's h. Okay, this axis is the y-axis. What axis is this here? This is actually the u-axis, where we're representing how big the velocity is, which is a little bit strange to think about, but you can take graphs that are like this and you can turn it like that. That's perfectly fine. And let's try to get some numbers up there. So what about u at 2.5? Well, going up here, u at 2.5 would be up here like this. We've got a no slip condition, so u at 2.5 would be 0. Okay, see if you can get 2 more points yourself. Maybe pause the video. Okay. So what about u at negative 2.5? That's the next easiest one, and that's going to be down there like that. Okay. And what about y equals 0? What about y equals 0? Well, that's the midpoint, and once the flow settles in, that's going to be the point where the maximum velocity is. So that's going to be 5 meters per second. So that's going to be 5 right there like that. Okay, and I've been a little bit lazy about my units. These are centimeters and these are meters per second. And for reasons that I'm asking you to accept on faith, but hopefully it seems reasonable, we get a parabolic velocity profile like that, parabolic velocity profile. And it would be good maybe if we just drew a couple velocity vectors in there to give a feel for what actually is going on. And if it had more time, I would do a nice job and get them nice and parallel. So that is the velocity profile like that. Okay, good. I'm just going to go ahead and pause and then move on to the last part, which is part C. So the last part is to figure out what's the pressure drop rate as this water goes down. And so we're trying to solve for this term right here, dpdx. And per usual, we'd like to do the algebra first and then substitute, but let's just talk about it a little bit and just go through that checklist. What do we know and what we don't know? Okay, well, mu we can look up. All right, h we know that's actually that 2.5 centimeters. So we got that, and we want to solve for this dpdx. Okay, but it's looking like we're a little bit strange situation because we don't know this y and we don't know what u at y. But if you think about it, we actually have enough information to get this done. U at y is a function. So for example, we know that if we put 2.5 in here, 2.5 centimeters, that this u would be equal to 0. And the equation will zero out. Well, that's correct mathematics, but it's not going to get us what we want. We have another value we can use, and that's at that midline line. What is the u value right there? And that's 5 meters per second. Okay, so at y equals 0, u is equal to u max, and that's going to allow us to take this equation and rewrite it and see if we can get it done. So I'm just going to rewrite this equation with y equals 0, and this is u max, and we'll take a look at it in just a second. So there's the equation rewritten, substituting y equals 0 and u equals to u max, and now it's not looking that hard. So certainly we could substitute the numbers, but I think the next thing to do is to do a little algebra and get dpdx. I'm going to do it on the whiteboard and encourage you to do it yourself. So see if you can get through it. Okay, so there we go. So there's the algebra. We need the viscosity, we need u max, and we need h squared. And it's kind of interesting, we get a negative in there. So all these numbers should turn out that we should get a negative. And what would that tell us? Well, dpdx is the rate of change of pressure as the water goes down in between those two plates. And what that's saying is that the pressure is going to decrease. That water is going to be losing energy. It's going to be losing pressure. If we want to get it through that plate over here, that water better enter pressurized. So what is that pressure rate? Well, let's just go ahead and substitute. And I'll get the numbers there really quickly. And I encourage you to pull out your tables and work that yourself. We're just going to use the standard values for water. And I do think it's good, because this is our first time using this formula, to fill in units and make sure that that all works out. Okay, so there's the numbers filled in. There's the numbers filled in, and the units are going to work out. We'll check that in just a minute. Ideally, we would check the units first before we got going, but I'm just going to go ahead and crank through the numbers. So I encourage you to pull out your calculator and let's see if we get the same thing. Okay, I'm getting about 18. To be precise, my calculator is giving me 17.92. I'll get that up there. So hopefully, you know, sometimes I make a mistake in class, and maybe I didn't make a mistake, made a mistake here. Bottom line is the process is right, but of course, please feel free to email me, and that would be nice if there is a mistake, and I can alert everyone else. Okay, let's work on units now. So we want how its pressure changing. So we would like this to have a newtons per meter squared per meter. So let's just see if we can get that in there. So taking a look at the units in this expression we have right here, if you take a look at the viscosity unit, you've got a newton meter per meter squared like that. So we would like to leave that in there because it is a pressure drop, newtons per meter squared. And please excuse my writing. I'm sort of writing. That's not bad, newtons per meter squared. Okay, what's left then? We're going to cancel out anything that could go away. So fortunately, the seconds go away. That's good. Okay, and I have a meter here, and I have a meter squared down there, so we're going to be left with a meter in the denominator. And that's exactly what we want. We have 17.92 newtons per meter squared, or put better, 17.92 pascals of pressure loss per meter. And there's our answer. And what does that mean actually physically for this situation? Well, we better, if this, let's say like this passageway was 10 meters long, we were trying to get through that water, through a passageway 10 meters long, there would be a loss of 17.92 pascals per meter. 10 meters, that'd be 179 pascals that it would lose, and we would need to make sure we got enough pressure here to accommodate that pressure loss. Okay, good. Well, that's it for today's lecture. Again, I'm sorry that it's taken me a while to get them up there. You want to work your way through this lecture, and then high priority right now is over this weekend or this next few days is to get homework number 7, as much progress as possible on it. And I will be trying to do the work that I need to do on my end, getting you some solutions to homework number 6 and some answers added to number 7. So feel free to email me. You guys take care and be safe.